In this video, we're going to talk about how to go through some examples that use the empirical rule or Tchebychev's theorem to answer the question. So here's our example. We know that test grades are normally distributed, and I see this phrase, normally distributed, and that's telling me I can use the empirical rule, and we're told we have a mean of 60 and a standard deviation of 8. Okay? So here is my bell-shaped curve. Always in the center of my curve is where the mean is going to be. So that's my mean, and I'm typing in 60. I'm actually going to refer to the cell that has the 60 in it already. So I have 60 here. And then one standard deviation below the mean would be this number minus the standard deviation. Again, we can put this 1 times in here. We can lock the reference to this cell. We can lock the reference to this cell. And the reason I'm locking these references is so that when I drag this to the left, I'm still referencing this cell and this cell, okay? And all I have to do is change one standard deviation to 2, and then 2 standard deviations to 3. And I can do the same thing here. I'm going to reference this cell, lock the reference. I'm going to add 1 standard deviation, lock the reference to that cell too. I can copy and paste. Now I know you can do these calculations in your head, but it's always good practice to use formulas so that if any of our data updates, or if we realize we made a mistake and maybe we just recopied the mean and the standard deviation incorrectly, I can just change these 2 parameters and all of a sudden everything else updates for me automatically. All right, so we want to know what percent of the test scores were between a 52 and a 68. Well, 52 is here, 1 standard deviation below. 68 is 1 standard deviation above. So this is data that's within 1 standard deviation, which we know is 68% from the empirical rule. And I've broken down these percentages here so that you know how much is in each area. So this is 2.35% here, because if you take 2.35 and 2.35, you get 4.7, which is the difference between 95% of the data and 99.7. So if we're adding another 4.7% between 2 and 3 standard deviations, and we divide that into 2 equal parts, we get 2.35. This gives me 13.5%, again, because there's a difference of 27% between 68 and 95%. 27 divided by 2 gives me 13.5. And 68 divided by 2 equal parts gives me 34% in each of those sections. Okay, so we know that within 1 standard deviation, there's 68% of our data. So the answer to the first question is 68%. And again, it never hurts just to put a little approximately 68%. Okay, we don't know it's exactly 68%, but it's going to be approximately 68%. Okay, so now we want to know the test scores between 44 and 60. So 44 is 2 standard deviations below the mean, and 60 is the mean itself. So I'm actually looking for the area under the curve between here and here. I wish that were straight. So I'm looking for this area in here, which I know from the diagram I have over here, this area is 13.5. That's not as bad as I thought it was going to be. Oh, it's getting worse. So we have 13.5%. Oh, wow, that's terrible. And then over here in this column of data, right in here, this is 34%. 13.5 plus 34%. And you might even want to let me know where you're getting your numbers. So we're going to do 13.5 plus 34% gives me 47.5%. If you want to change the type of number, you can just change it to, that didn't work. You can just put a percent. You can't. When you're using a formula, if you then change it to a percent, it's not going to give you the right number because it's moving the decimal place over twice. So let's just leave it at, or we can change this to be 0.135 and change this to be 0.34. But now it's rounding to the whole number value. So Excel, as great as it is, doesn't always do everything you want it to do immediately. So all I did here was I clicked on increase decimals so that at least we're getting 2 decimal places, or we're getting 1 decimal place here. And now I want to know what percent of test scores are below 60%. Now you might think that you should add up 34 and 13.5 and 2.35, but remember, there's more data out here. There's another 0.15% of data outside of 3 standard deviations, because 0.3 divided by 2 means 0.15% over here and 0.15% over here. So over on this side, below the mean, if we add up 34, 13.5, 2.35, 0.15, we're actually going to get 50%. 50% of our data falls below the mean. 50% of our data falls above the mean. So for normally distributed data, 50% of the data is always, the mean is always the halfway mark. It's the 50th percentile. Half the people got below that, half the people got above that. So now, looking at Tchebychev's theorem. This is not normally distributed. It doesn't say anywhere in here that it is normally distributed. It just says the average annual income per family in Connecticut is $680,000 with a standard deviation of 1.2 million. Now you might think $680,000 is very high. It is, but that's because this data are skewed, because most people make less than that, but some people make way more than that, and those few people that make a lot more than that skew the mean to the right, which makes the mean much bigger. I think the median income in Connecticut is like $80,000 for an individual. So for a family, it's probably around 130, something like that. I'm not sure exactly on that data. I haven't looked it up. But we have 680,000 is our mean. We have our standard deviation is 1.2 million. Too many, right? I get it right that time. 1, 2, 3, 1, 2, yeah. All right. Now, we want to know, find the smallest percentage of families that would fall within 2 standard deviations of the mean. Now, because this is not normally distributed, and it doesn't say that it's normally distributed, so I can't assume that it's normally distributed, all I need to do is apply Tchebychev's theorem. So over here, I'm going to do 1 minus 1 over k squared. So 2 standard deviations would be 1 divided by 2 squared. We know that 75% of our data would fall within 2 standard deviations of the mean. At least. That's the smallest percentage. I think that since 1.2 million brings us actually past 0% or $0, that almost all families would fall within 2 standard deviations of the mean. I think it would all fall within 1 standard deviation of the mean. But Tchebychev's theorem guarantees that at least 75 would. If it were 5 standard deviations, 1 divided by 5 squared, we're guaranteed 96% of people fall within 5 standard deviations of the mean for this problem. Now, notice it didn't even matter what the mean and standard deviation are for this problem. I didn't need to use it. Needed to use it here, but I don't need to use it here. All right, I will see you in the next video.